In this video, we're going to discuss sketching polynomials, and let's start with a couple of definitions. So here's our first definition here. So we'll say that if we look at the picture on the left here, we've got a function that is increasing. So we say f of x is increasing if the derivative is a positive number. So I'm just going to rearrange the way that I'm writing that. So we can see that when you look at this curve here on the left, if you pick any point on there and you draw the tangent line, slope of that tangent line is going to be positive because the curve is going up as we look at it from left to right. So we say in that situation, f of x is increasing, and the way we can identify that is if f prime of x is a positive number. In the picture on the right, we've got the opposite sort of scenario. As we run along this curve from left to right, let's imagine doing that, the y values are actually decreasing. So we would say that our function is decreasing, y values are getting smaller as we go from left to right. And the way we can identify that is, again, talking about the slope of the tangent line. So if we pick any point on that curve, let's say this point here, and we draw our tangent line, slope of the tangent line is now going to be negative. So we can say f of x is decreasing if f prime of x is negative. I think that's a more logical way to write our definition. So derivative being positive tells you that your function is increasing near that point. Derivative being negative tells you that your function f of x is decreasing near that point. That's our first definition. Second definition, we're going to define two important concepts here, and that's the idea of a relative maximum and a relative minimum. So first of all, let me give you an intuitive idea of what a relative maximum is. So a relative maximum is a point on a curve that is a hilltop. Formally, you know you've got a relative maximum when you're running along your curve from left to right. Your function moves from increasing and then switches to decreasing. So that point there is called a relative maximum. The opposite sort of behavior is if you have a relative minimum. And you could call this intuitively, I suppose you could say that's a valley, or more specifically, you might want to say the valley floor, the very bottom of the valley. So here's our relative minimum point on this picture. And if we were trying to be rigorous about this and use some of our terminology from calculus, we would say, well, a relative minimum is a point where your function moves from decreasing to increasing. So as we read from left to right, here our function is decreasing, the y values are getting smaller. At the relative minimum, that behavior stops. And then just to the right of that point, the y values start to get bigger again. So remember that the title of this section was called Sketching Polynomials. And the title is a little misleading because these days, if we want to sketch a polynomial, we just hop over to Wolfram Alpha, type in the equation of the curve, and Wolfram Alpha spits out a graph. So it's not actually the graph of the polynomial that we're so interested in. It's actually finding these relative maximum and relative minimum points on the curve. Because often in the real world, you're trying to maximize or minimize something. You're trying to minimize cost, or you're trying to maximize the volume of a certain geometric shape or something like that. We'll actually talk in more detail about that in our next section. But for now, as we go through this discussion, let's just keep in mind that finding these interesting points, these relative maximum, relative minimum points on a graph is really our ultimate goal here. So with that, we're going to write down one more fact, and then we can jump into a big example. So our fact is that x values, where f prime of x is equal to 0, are called critical points. So we can think of that part as a definition. Critical point is a place where f prime of x is equal to 0. And the reason why we care about critical points is because they are possible relative maximum or relative minimum points. So sometimes I'll just write relative max instead of relative maximum, relative min instead of relative minimum. So these critical points are possible relative max or relative min points. That means if you're trying to figure out where the relative max or relative min points are, you go ahead and find your critical points, and then you have to do a little bit more investigation. So why do we have to do more investigation? Well, that's because critical points can really have 4 possible kind of behaviors around them. So the first sort of behavior is this could be a critical point, and that actually does correspond to a relative minimum point. You could have this sort of behavior where the function is increasing and then begins to decrease on the other side. So that's a relative maximum. But you can also have critical points that don't turn out to be relative max or relative min points. And then the curve would look like this. You might have something like the curve does this sort of thing, but then continues to increase just at a faster rate on the other side. Or you could have this sort of behavior where your curve is decreasing pretty quickly, and then it moves into a slower rate of decrease. So these last two are neither relative min nor relative max points. So the main takeaway here is we're defining what a critical point is. It's a place where f prime of x equals 0. Why do we care about critical points? Because they may lead us to relative max or relative min points. So with all that sort of definition and theory out of the way, we're ready to just jump into a bigger example. The problem is to find all relative maximum and relative minimum points for this particular function, f of x here. So the first part of the process is that we're going to find the critical points. So what that means is we are going to set f prime of x equal to 0. So by definition, a critical point is an x value where f prime of x is equal to 0. So we're going to find those critical points, and then there will be a follow-up part to the question where we explore those critical points in a little bit more detail and figure out whether they really are a relative maximum or a relative minimum. Okay, so let's take f prime of x first of all. We get 6x squared minus 18x minus 240. And then what we want to do is set f prime of x equal to 0. So we're going to set 6x squared minus 18x minus 240 equal to 0. And typically that's going to involve some factoring. So we can actually pull out a 6 from each of these coefficients here. That would leave x squared minus 3x minus 40 in the brackets there. And that will work out nicely because now we're looking for a couple numbers that multiply to negative 40 and add to negative 3. So we could use negative 8 and plus 5. Okay, so we get that factored. And then once that's factored, then we can figure out what our solutions are going to be. So if this left side has to equal 0, x could equal 8 or negative 5. So these x values here, those are called our critical points. So they are places where f prime of x is equal to 0. So just as a recap of what we said on our last screen, now that we know that these x values are critical points, we know they fall into one of 4 categories. So around this x value, x equal 8, the curve could be doing this kind of thing, it could be doing this kind of thing, it could be doing that kind of thing, or it could be doing that kind of thing. We're only interested in these first 2 cases. So we need to do a little bit more exploration to figure out whether x equal 8 or x equal negative 5 are a relative maximum or relative minimum, and if so, which one they fall into, whether they're maximum or minimum. Let's talk about these critical points in a little bit more detail. So these 2 critical points here, these are the only x values where f prime of x might change sign. Because in order for f prime of x to move from being a positive value to a negative value, it would have to go through 0. Or in order for it to go from negative to positive, it would have to go through 0. So these critical points are the only x values where f prime of x might change sign. But the caution is that the sign change is not guaranteed. So what we're going to do is we're going to make a number line, just representing all the different x values from negative infinity to infinity, and we're going to put our 2 critical points on there. So our critical points were x equal negative 5 and x equal 8. Okay, now what we're going to do is we're going to investigate what's going on with f prime of x in each of these intervals. So these 2 critical points actually divide the number line into 3 little intervals. And we're just going to investigate the sign of f prime of x in each one. So for example, you might see something like f prime of x is negative for all these values, positive for all these values, and positive for all these values. For example, we'll do some investigation in a minute. So if we can figure that out, then that will tell us whether we've got a relative maximum, a relative minimum, or neither at each of those critical points. Okay, so that's the plan. So the way you figure out what's going on with f prime of x is you're going to test a value in each interval. Now, what's really interesting here is that you only need to pick one number in each interval to figure out what's going on in the entire interval. So let's look at this first interval from negative infinity to negative 5. Okay, we can pick any number in here. I would say, it could be negative 6, could be negative 7. So test some number, and what you're doing is you're plugging it into f prime. Okay, so let's just look back up a little bit higher up on the screen here. I've got f prime of x highlighted. So let's make sure we know where that is. And let's plug in negative 6 into this. Okay, now all we care about is just the sign. So put negative 6 in there, and what you'll find is that comes out to a positive number. So f prime of negative 6 is positive. I'll just write that over on the side. Okay, what that tells us is that f prime of x is positive on this entire interval. So it's now guaranteed that if you plug, negative 8 into f prime of x, positive number is going to come out. Guaranteed that if you put, say, x equal, negative 1,000 or something into f prime of x, you're going to get a positive number. So why is that guaranteed? That's because the critical points are the only x values where f prime of x might change sign. So the only places the sign change can happen are here and here. Therefore, just testing one value in each little interval is enough to tell you what's going on in the entire interval. So that's really powerful. Okay, let's take a look at this middle interval now. We're looking at this section of x values between negative 5 and 8. So choose any number that you like in there. You wouldn't want to choose negative 5 or 8 itself. You want something that's strictly inside the interval. I would say 0 would probably be an easy choice to work with. But some people might choose 1, or you could choose negative 4. Anything that's between negative 5 and 8 is going to work. Okay, so let's say we choose 0. Look back up here at the top where we've got f prime. So plug 0 into f prime, and again, you're just checking, do I get a positive or negative number? You get a negative number. Okay, so because f prime of x is not changing sign anywhere in this interval, that tells us no matter what x value we plug in this little interval here, we would get a negative number. So f prime of x negative all the way through there. And then same deal for the last little interval here. We're talking about x values that are bigger than 8, so choose any number that you like. Maybe you want to choose 9 or 10 or something like that. Plug that into f prime and you get a positive number. So what that tells us, f prime of x is positive for all of these x values. So again, just testing a single value in each interval tells you what's going on in the entire interval. And it's not possible for f prime of x to change sign anywhere in that interval because these critical points that we've got up at the top of the screen are the only places where f prime of x might change sign. A second sort of follow-up comment here is sometimes what people will say is they'll say, okay, well, why can't I just figure out, the left sign here? Why can't I just start on the left interval and say, okay, that's positive, and then just let the signs alternate from there? Well, the caution here is that the sign is not guaranteed to change. So it's not guaranteed that you're going to see this plus, minus, plus pattern. Often you will. But we shouldn't fall into the trap of thinking that the signs are always going to alternate, because sometimes you'll see something like plus, minus, minus or something. And I'll actually show you examples of that later on in the video. So yes, we really do need to investigate each of the intervals. If you've got 2 critical points, you've got 3 intervals that you need to separately just do a little test value for. So all this stuff right here, that's sort of discussion, because that's the first time that we're doing this sort of problem. But in a typical problem, once you had found your critical points, what you would do is you would draw your number line just as we did. Put your critical points on there, so the -5 and 8. You would test a value in each interval and figure out the sign of f prime of x, just like we did. So we got plus, minus, plus, like that. And then what we usually do underneath that is we just write down, what does that mean for our function f of x? So remember that if f prime of x is a positive number, that means that our function is increasing. And if f prime of x is a negative number, as we've got in this middle interval here, that means that f of x is decreasing. Okay, and then for the third interval, we're in the other situation, f prime of x is positive, so that tells us that our function is increasing. Okay, and that increasing, decreasing behavior is what we really care about in terms of finding a relative maximum or relative minimum point. So let's just draw a picture underneath here of what's happening. So let's say this is your x value, -5 right here. What we know from our discussion is that our function is increasing before we get to -5 and then decreasing afterwards. So that tells us we've got a relative maximum at -5. The way I usually draw that, I don't usually bother drawing the axes or anything like that. I just think about, okay, what happens if your function goes from increasing to decreasing? That's a relative maximum. And then at x equal -8, we've got the opposite behavior. The function goes from decreasing to increasing. So let's write out our answer just at the bottom of the screen here. The original question just asked us to find all relative maximum and relative minimum points. So we can say we have a relative maximum at x equal -5, and we can say we've got a relative minimum at x equal 8. Okay, now if we were going to actually go and sketch a graph, which we will do a little bit later on in the video, sometimes rather than just giving an x value, we'll actually give a pair of coordinates. So we'll give an x and a y value together. And if you want to do that, to figure out the y value that goes with your particular x value, you would need to go back to your original function. Okay, so we could scroll back up to the top of the page. See, the original function that we were investigating, we haven't thought about it in a little while. It's this 2x cubed minus 9x squared minus 240x plus 5. So if you wanted the y value that would actually go on the graph, you would take -5, put it into your function, and you'd get 730. Okay, and then similar thing, if we wanted a point that was on the graph, if we wanted to describe our relative minimum in terms of an x and a y coordinate, we would say, well, the x coordinate is 8 and the y coordinate is what we get if we put 8 into our original function. And that would be -1467. So let's just run through this quickly again, now that we've seen the overall idea. So what did we do to find our relative maximum and relative minimum points? Well, we took our derivative and then we set it equal to 0, and that gave us some critical points. Okay, then once we had those critical points, let's see the clean version of what we did. We built this little table here with our different critical points, and we figured out the value of f prime in each of those little intervals, and then we wrote down what does that mean for f. Then at the end of the problem, we were able to say that we had one relative maximum point, meaning a hilltop, and we had one relative minimum point, which is like a valley floor. And if you want to describe those in terms of both an x and a y coordinate, then you would want to go back to your original function to figure out the y coordinate, because you're actually thinking, oh, if I were to, actually sketch this graph, which is the graph of y equal f of x, we're trying to describe a specific point that would be on that graph. So it would be appropriate to use the f value, not the f prime value, the f value to get the y value there. So we're going to do a couple more definitions here. We're going to get into a discussion about the second derivative and see how that can help us in making sketches of polynomials. So here's our definition. So let's look at these two curves that we've got in our picture here. In the left curve, you could imagine this looking like a bowl that's right side up. And in the curve on the right, you could imagine that's looking like a bowl, which is upside down. So imagine you were, trying to eat cereal out of this bowl. In the left picture, right, the cereal would be in the bowl. In the right picture, the cereal would be on the floor because the bowl is upside down. So the proper terminology that we use for this, we say our function is concave up when the bowl is pointing upwards, and we say that f of x is concave down if the cereal is on the floor, if the bowl is upside down. The way that we're going to recognize whether our function is concave up or concave down is using the second derivative. So if we wanted to turn this into a definition, we could say f of x is concave up if f double prime is a positive number. So f double prime being positive corresponds to concave up, and that corresponds to this sort of picture here, where you can eat cereal out of the bowl. F of x being concave down, we could say that happens if f double prime is a negative number. So if f double prime is negative, f of x is concave down, and that corresponds to a situation where your cereal is on the floor. So talking about the second derivative can help us get the shape of the curve right when we're doing a sketch. Okay, now it might be nice to have a name for a point where we switch from being concave up to concave down. That's what our second definition is going to give us. So a point where we switch from being concave up to concave down is called a point of inflection, or some books call this an inflection point, same thing. So you can imagine a curve that does this sort of thing. So your cereal's in the bowl, and then, all of a sudden your cereal's on the floor. So this point here would be a point of inflection. I'm writing CU and CD for concave up and concave down. And we could have the opposite sort of situation, where maybe our curve is concave down for a while, and then at some point the concavity switches and we move to being concave up. So this blue point here, that's our point of inflection. So those points can be helpful when we're making sketches. And if we think from an algebra point of view, how are we going to find these points of inflection? Well, let's look at this fact here. So points where f double prime of x is equal to 0 are possible points of inflection. So if you wanted to find points of inflection, what you would do is you'd set f double prime equal to 0. Those are your possible points of inflection, and then you'd have to just do a little bit more investigation to figure out whether they really are points of inflection. And that little bit more investigation would involve just making a table, as we did in our previous problem. So we are going to find all points of inflection for this particular polynomial, and that may look familiar because that's the same polynomial that we worked with in our first example. Main thing to realize here is that that's going to involve the second derivative. So we're going to calculate f prime, and then we're going to calculate f double prime. Let's try that. So f prime is 6x squared minus 18x minus 240, and f double prime is 12x minus 18. Okay, so to find your points of inflection, what you're going to do is you're going to set f double prime equal to 0. So 12x minus 18 equals 0, and we'll just figure out what x values come out of this. So 12x is equal to 18. In other words, x equals 18 over 12, or we could probably better simplify that fraction just to keep the numbers nice and simple. So if you divide top and bottom by 6, let's call that 3 over 2. Or you could even say 1.5 because it's exact as a decimal. So again, we're going to have the same kind of discussion as we had in the previous example. So these numbers, in this case, there's only one number on that list, but in general, you might have a couple numbers on that list, are your possible points of inflection. So they're not guaranteed to be points of inflection. We have to do a little bit more investigation to figure out whether they are points of inflection or not. So let's think of it this way. These x values on your list are the only x values where f double prime can change signs. So at all the numbers on this list, f double prime is equal to 0, and that's the only place where f double prime can switch from being positive to negative or vice versa. But the caution is that a sign change is not guaranteed. So we're going to make a table of values. We're going to draw our number line. And in this case, there's only one x value to put on here. So we'll just say this is 3/2. What we want to investigate is the sign of f double prime in these different intervals. So if you've got one x value on your list, that divides your number line into 2 different intervals that we're going to investigate. We're going to figure out what's going on with f double prime, and then we can draw a conclusion about our function f. So let's look back at f double prime. Always good to have that highlighted. It is 12x minus 18. So choose any real number that you like in this left interval here. So it can be anything that is less than 1.5. It could be 1, it could be 0, it could be negative 100, and plug that into f double prime. So I would say, okay, I'm going to choose 0. That seems easy to me. So f double prime of 0 is going to be a negative number. So I'm going to write a negative sign here. And what that tells us is that no matter what x value we had chosen along here, guaranteed we would get f double prime equal to a negative number. Why? Because 3/2 is the only place where f double prime can potentially move from negative to positive. So it's good enough just to test any number, any one number that you like in your interval, and that tells you what's going on in the entire interval. So f double prime being negative tells us that our function is concave down. So everywhere for all these x values that are less than 3/2, our function is concave down. Okay, now let's jump over to the other interval. We can pick any x value that we like as long as it's bigger than 3/2. So you could choose 2, you could choose 5, you could choose 10. I guess I would probably just choose 2. Put that into f double prime, and that comes out to a positive number. So plus, and that tells us that our function is concave up for all of these x values in this interval here. Okay, now the caution that we talked about before comes up again. The signs are not guaranteed to alternate as you read through this table. So just because your first sign here was a negative, that does not automatically tell you that the next one's going to be positive. Often the signs will alternate and they'll flip back and forth between negative and positive, but not always the case. So you do have to do a separate test value for each of your little intervals. If you have 2 intervals, you have to test 2 numbers as we did over on the side here. Okay, but now we have got enough information to pretty much finish this up. So if we were to just sort of draw a picture of what's going on with our function, we're told that our function is initially concave down, so Cyril's on the floor, and then at some point it switches to being concave up, so something like this. Concave down, concave up. So that point right there is a point of inflection, and that point right there has x value 3/2. So let's write down our answer just at the bottom here. The question was to find all points of inflection. We have one of them. So we have a point of inflection at x value 3/2. And if you want the y value that goes with that, you need to go back to the original function. So that when we actually plot the graph of our function, we're interested in what point lies on that function. So you'd look back at your f right from the beginning of the problem. If you like, for this particular problem, because 3/2 is exact as a decimal, that probably makes life easier when we go back in to plug into our function f. And if we scroll right back to the beginning of the problem, here's the function f that we're talking about. So that cubic polynomial there. So if you plug 1.5 into that, you get negative 368.5. So that is our point of inflection. So in this example, we're going to sketch this same polynomial that we worked with over our 2 examples. And really what this is going to do is just give us a visual feel for all the work that we've just done. So I'm going to collect all the work that we've done so far. We found a relative maximum point and a relative minimum point for this function in our first example. And then in our most recent example, we found a point of inflection. So we're just going to collect all of that information here, and then we'll do our sketch. So looking back over our work from the first example, we found a relative maximum point at -5, 730, and a relative minimum point at +8, and -1467 was the y value to go with that. And most recently, we just found a point of inflection, which had coordinates 1.5 and -368.5. Now, there's one other point that's pretty easy to get, and that is the y-intercept. That doesn't involve any calculus, so we'll just do that quickly here. So to get the y-intercept for any function, just take x equals 0 and plug it into your function. So if we plug x equals 0 into f, we get an f value of 5. In other words, we get the point 0, 5. So the reason that works, if you're just trying to think about where does our function cross the y-axis, like here, you're just thinking about what point has x value 0. So plug x value 0 into your function. That gives you the coordinate of your y-intercept. So if we wanted to make a sketch of our function, really these are the 3 different categories of things that would be helpful. The y-intercept is helpful. Finding any relative max or relative min points is helpful, and finding points of inflection is helpful. So now that we've done all that work, let's just put it together into a sketch. So we'll do our sketch down here, and always good to think about what a good scale would be. So if we look at our y values, we're going to have to go as far down as about -1500 and up as far as 730. So probably going in increments of 500 or so, I would say would, allow everything to fit on here nicely. So that's 1,000, that's -1500. And then feel free to use a different scale for your x-axis, right? For the x values, we need to go from -5 to 8. So maybe if you go in increments of 2, that would work pretty well. And then always good to label the axes as well. Okay, so we got our scale on there, we got our axes on there, and let's just start to plot some points. So -5, 730 would be about here. 8, -14, 67, let's say is about there. X value 1.5, well, because we're going up in increments of 2, 1.5 is about there, and we want to be around -400-ish. And then last point is our y-intercept at 0.5. Well, because of the scale on the y-axis, that's basically just going to look like the origin. So there we go. Okay, and then let's think about it. So this point, -5, 730, just draw it in blue here so we can see where we're looking. That's a relative maximum. So in other words, a hilltop. So that tells us that our function is coming up to that point and then decreasing after that. Okay, and then it's going to go over as far as 0.5. So it's doing something like that. And by the time it gets to this point here at x equal 1.5, that's our point of inflection. Okay, so our function is actually concave down till we get to that point. But this point here being the point of inflection tells us, oh, serial switches from being on the floor to now in the bowl, right? So the way that we're drawing the curve is going to change. Now we're drawing it sort of like this, so that serial is in the bowl. We're coming down to this point here, which is the relative minimum. So that's like the valley floor, and then the function will increase from there. So if you like, you might find it helpful just to draw like a little arrow and say that's a relative max. That right there is a relative min. And this point right here was the point of inflection. So here's our last example to test our understanding for this section. We've got a function given to us, and we're going to find 4 things. We're going to find the y-intercept. We'll find all relative maximum or minimum points. Then we'll find all points of inflection, and then we'll find or make a quick sketch at the end. So part A, let's start with y-intercept. That's the easiest part. So take x equals 0, plug it into your function, and figure out what your y value looks like. So you can either call this f or you can call it y. Plugging 0 into our function, we get 0. So that tells us our y-intercept is 0, 0. Great. That'll be helpful when we make our sketch. Part B, we're going to find all relative maximum or minimum points. Okay, so let's write ourselves just a general kind of procedure for how to do this. So for relative maximum or minimum points, you want to set f prime of x equal to 0. And that gives you not exactly your relative max or min points, but your possible relative max or min points. So we then need to make a table to follow up to figure out whether those points really are relative max or min points. Okay, so let's do it. Let's calculate f prime of x. So we've got our function up at the top of the screen here. F prime of x is going to equal 6x to the 5th minus 60x cubed, and we want to set that equal to 0. So 6x to the 5th minus 60x cubed equals 0, and then there will be some factoring involved. So let's factor out a 6x cubed. That will leave us with x squared minus 10. And then if you like, you can factor that x squared minus 10 as x minus root 10 and x plus root 10. Okay, so there are going to be 3 different x values here that solve that equation: 0, positive root 10, and negative root 10. So these are possible relative maximum or relative min points, but the way we're going to tell for sure is we're going to make a little table. So when we say table, we mean draw the number line, put your x values on there. Okay, so they should be in order. Negative root 10 would be here, 0 would be there, root 10 would be there. And what we need to figure out is whether our function is increasing or decreasing along each interval. So we're going to talk about f prime values, and then we're going to talk about what that means for f. So the idea is that these 3 critical points that we found, let me just identify them here on the number line. So these 3 critical points that we found divide the number line into 4 sections, or 4 intervals, you could say. So we need to do a little test for each of these 4 intervals, and we just need to figure out whether f prime is positive or negative on each interval. So let's highlight our f prime of x and let's figure this out. So take any number that's less than negative root 10. Okay, so you could choose something like negative 4 or negative 5 would be a good choice here. Plug that into f prime and just figure out what the sign looks like. So it will come out to a negative number. No matter what number you choose in this interval, you're going to get a negative number, and that tells us that our function is decreasing over that section of the x-axis. Okay, and then we're going to do a similar thing for this interval here now. We're looking at the numbers strictly between negative root 10 and 0. So maybe you want to choose negative 1 or negative 2. Put that into f prime, which we've got up near the top of the screen here, and that comes out to a positive number. So that tells us that our function is increasing through all of those x values. Okay, now next we want to choose an x value somewhere between 0 and root 10. So I would probably choose 1, but you could choose 2 or 3 if you wanted. F prime will come out negative there. So that tells us that our function f is decreasing for all of those x values there. And then finally we pick a value where x is bigger than root 10. So that could be something like 4 or 5 or 6 or something like that. Put that into f prime and we get a positive number. So that tells us that f is increasing for all of those x values. So again, we're seeing this alternating sign pattern where the signs go negative, positive, negative, positive. Unfortunately, they don't always perfectly alternate, and we'll actually see that when we get to part C of this example. So yeah, you do really have to investigate each of the 4 numbers. You can't just do one and then sort of draw a conclusion about the others, unfortunately. Okay, so while we've got this table in front of us, let's actually figure out whether we have some relative maximum and relative minimum points. So let's think about what's going on around x equal -10, or negative root 10 rather. So look at the behavior of our function. It's going from decreasing to increasing. So that's this kind of behavior. So that means we have a relative minimum at x equal minus root 10. And maybe we'll figure out the y value in a minute. Okay, let's look at our other points just while we're looking at this table. So at x equals 0, what kind of behavior do we have? Well, the function's going from increasing to decreasing. So that's this kind of behavior. Function is increasing and then decreasing. So we have a relative max when x equals 0. And then finally for our last x value over here. So for this x value, x equal root 10, let's think about what the function's doing on either side of that. It's going from decreasing to increasing. So decreasing and then switches to increasing. That tells us we've got a relative minimum when x equals root 10. Okay, so 2 relative minimum points, 1 relative maximum point. And then let's figure out the y values that go with that, just so that when we go and make our sketch later, we're ready to do that. So when you're actually writing down the coordinates of your relative minimum and relative maximum, you're thinking about, when we actually make the graph of this function, what are the points going to look like? So the y values are coming from plugging into your original function right from the beginning of the question. So to get this y value here, you'd be going f of negative root 10. Here you'd be going f of 0. And here you'd be going f of root 10. So we can scroll right back up to the top of the problem just to remind ourselves what f was. I think I'll just put that in a purple box so that we can find that again later. So if you put negative root 10 into that, you would get negative 500. If you put x equals 0 into your original function, you would get 0. And then if you put positive root 10 into our original function, you would get negative 500. So we've now determined that we have 2 relative minimum points, we have 1 relative maximum point, and we've actually figured out the y values that go with those by putting them into our original function. So that's part B done. Now we're going to move into part C, which is finding any points of inflection. So I think in the upper right corner here, I'm just going to write down f and f prime so that we don't have to keep flipping back to the previous page. So our original function was x to the 6th minus 15 x to the 4th. And over the course of part B, we figured out that the derivative looked like 6x to the 5th minus 60x cubed. So what we're doing in part C is we're finding all points of inflection. And I think it would be a good idea just to write down a general sort of game plan for how to do that. So the points of inflection involve the second derivative. You want to set f double prime of x equal to 0. And when you do that, that's giving you your possible points of inflection, but you need to do a little bit more investigation to figure out whether they really are points of inflection. So you do a table to figure that part out. So here we go. Let's calculate f double prime. We've got our f prime sitting in the top right corner here. So just take the derivative again and you get 30x to the 4th minus 180x squared. And we want to take this and set it equal to 0. Okay, so if we factor out a 30x squared, that would work pretty well. That would leave us with x squared minus 6. And then we could factor that x squared minus 6. We could think of that as x minus root 6 times x plus root 6. And that way we'd get all our x values here. So x could either equal 0, positive root 6, or negative root 6. So let's just label these here. These are our possible points of inflection. And we're going to make a little table to investigate them further. So this line here represents our number line. Let's put our 3 x values on there, and they should be in numerical order. So minus root 6, then 0, then root 6. And when we're talking points of inflection, we're really interested in figuring out the sign of the second derivative, and then we'll write down what that means for our function. Okay, so we've got our second derivative sitting up at the top of the screen here. And let's notice that these 3 possible points of inflection, just draw dots there on the number line, those 3 points of inflection are going to divide the number line into 4 intervals. So we have to do 4 little tests here of plugging into f double prime. So let's choose a number that's somewhere in here, something that's more negative than negative root 6. You could choose like negative 3 or negative 4. And we're putting it into f double prime. So that's going to give us a positive number. And second derivative being positive tells us that our function is concave up. So it tells us how our curve is curving. Okay, then for the second interval, you're looking for a number that's strictly between negative root 6 and 0. So maybe something like negative 2 or negative 1 would be a good choice there. So pick a number there, plug it into f double prime, and you get a negative number. So that tells us that our function is concave down for all the x values between negative root 6 and 0. Okay, then we go over to our third interval. Pick any x value that's bigger than 0, but less than root 6. So maybe you want to choose x equal 1, for example. Put that into our f double prime that we've got up at the top of the screen. And that comes out to a negative number. So notice this is the first time where we've seen the signs fail to alternate. We got the same sign twice in a row. So this is just to caution you that this can happen. It doesn't happen very often, but it can happen with either the first or the second derivative. So that's why we have to be careful and really do a test for each little interval. Okay, so no matter what number between 0 and root 6 you choose, f double prime comes out to a negative number. That tells you that the function is concave down for all of those x values. And then one more little test here. Let's choose an x value that's bigger than root 6. So maybe you want to use 3 or 4 or something like that. Put that into f double prime, and that comes out to a positive number. So that tells us that our function is concave up for all of those x values. Okay, so with that table done, we can now write down our points of inflection. So you're going to have a point of inflection when the concavity actually changes from concave up to concave down or vice versa. So at negative root 6, got this behavior where we're moving from concave up to concave down, which in our sketch you can think like this. So cereals in the bowl and then cereals on the floor. So negative root 6 being that point on that x value there where the concavity switches. Okay, and then at x equals 0 is not a point of inflection because the concavity does not change there. But at x equal positive root 6, we do have another point of inflection because our function is moving from concave down to concave up. So second point of inflection when x is equal to positive root 6. If we just draw a picture of what that looks like, the graph at that point is moving from being concave down to then being concave up. So something like this. Okay, and then if you wanted the y values that go with this, if you were thinking about actually making a sketch of your function and thinking about any point that would be on that sketch, it would be the f of x value that you would be using for your y value. So in other words, whenever you're trying to get a point that's on your graph, you're always going back to your original function from the beginning of the problem. So we would figure out what f of negative root 6 is, and we would figure out what f of root 6 is. So we'll just scroll back up for a second to see where our function was. I think I had written it down right towards the top of the screen here. Yep, there it is. So x to the 6 minus 15 x to the 4th If you plug root 6 into that, you get negative 324. So the negative root 6 gives us the same value as the positive root 6 did. So that is part C done. We found our points of inflection, and then very last thing we're going to do to finish off this problem and to finish off the video is just to make a sketch putting it all together. So I think what I'll do is I'll just collect all the points that we figured out from the first 3 parts. So we had our y-intercept, we decided was 0, 0. We had 2 relative minimum points and 1 relative maximum point. So let's write down those coordinates just for the sake of making the sketch. So one was minus root 10 minus 500, and the other one was 0, 0. So those are our 2 relative minimum, and then our relative maximum was the positive root 10 comma negative 500. And then finally, we found some points of inflection. So the x coordinates were minus root 6 and positive root 6, and the y values that went with that were negative 324 for both of them. Okay, then the other thing you could do, just to make your life a bit easier in terms of sketching, maybe just over on the side, we want to have a ballpark of what root 6 looks like roughly and what root 10 looks like roughly, because we're going to be using those numbers a lot. So root 10 is about 3.2, so just a bit bigger than 3 in terms of the sketch. And root 6 is about 2.4 or 2.5, you could say, when we're doing the sketch. So just breaking this down conceptually, the y-intercept required no calculus. The relative min, relative max was all about the first derivative, and then the points of inflection were all about the second derivative. So we've sort of got 3 parts there that we had calculated, and now we can put it all together into a nice picture. So let's think about what scale we would like on our axes. Just scanning through the x values here, we're going to need to go as far as plus or minus root 10. So if we go about 4 units over in either direction, that should be perfect in terms of getting everything on there. And then in terms of the y values, we need to go up, or we need to go down as far as negative 500, and really just up as far as 0. So most of the interesting stuff is happening, or all of the interesting stuff actually is happening below the x-axis. Okay, so let's just do that. Let's say that's negative 500. We'll just go up in increments of 100. There we go. So let's start with just plotting all of our points. So we know we had the y-intercept at the origin. So I just realized that I just mislabeled some of the relative min and relative max points. So let's correct that quickly. We've got a relative minimum when x equals minus root 10. We've got another relative minimum when x equals positive root 10. And then we've got a relative maximum at the origin. So let's fix all this up. Okay, so I'll just highlight really the changes that I'm making there. So this is actually a max and that's a min. And I had it written the other way around. Just when I recopied it, I copied it incorrectly. So let's start to plot some of these points then. Just scanning through our list of points, we've got the origin was our y-intercept. That also happens to be one of our relative maximum points. We've got a couple of relative minimum points, and they happen when x is about 3 and negative 3. The y values are negative 500. Okay, so let's get those on there. About there and about there. And if you want, you can start to label some of your points. Like that's going to be a relative maximum. And these guys here are going to be relative minimum points. That might help us when we do our sketch. And then we've got a couple of points of inflection. So the points of inflection, just looking over here, points of inflection are at x values about negative 2.5 and positive 2.5. And the y values are about negative 300. Okay, so let's say we got one of those around here. And then another one, x is about 2.5 and y is just a bit bigger than negative 300. So about there. Okay, so those are points of inflection. So now let's see if we can draw a curve that's joining all those points and that has these properties that we've highlighted. So if this point here is going to be a relative minimum, then our curve must be doing something like that. And the fact that there are no other relative maximum or relative minimum points to the left of that tells us that our function must just be doing this. So there are no other hilltops or valleys to the left of that. Okay, now this point here is a point of inflection. So that tells us that the curve is going to be moving from concave up to concave down. So it's going to be switching to doing this sort of curving, going to come up to a relative maximum, and then it's going to be doing, again, this sort of curving until it gets to this point right here, which is a point of inflection. So now Cyril switches from being on the floor to in the bowl. So we're just getting sort of a steeper curve that's opening upwards now, coming down to this relative minimum. And then there are no other hilltops or valleys to the right of that. So that tells us our function must just be increasing from there. So that way we've made a sketch that incorporates really all 6 of those points. I say 6 points because our y-intercept happened to be the same as our relative maximum point. So that is all about how we can use the first and second derivative to help us sketch a curve and, most importantly, identify our relative maximum and relative minimum points. Thanks for watching.